Okay, so we're recording. We're going to cover the second half of chapter 9. So last time we covered basically the first half, static equilibrium. So just to kind of remind you, the static equilibrium portion, we summed up all of the forces to zero, and we summed up all of the torques to zero. We have to do this as vectors here. We didn't really look at torque as a vector, and we don't really have to in this class as long as we keep things kind of two-dimensional. But this is what we covered last time. So the next thing to do would be to look at how materials respond to forces. So if we have these two conditions right here, this implies we are in static equilibrium. The next logical question kind of to ask is, well, if we have like all these forces acting on these different objects, what if those forces are too big, so to speak, for the materials to handle? So like, you know, you have a building, right? The building is in static equilibrium, normal force balancing the weight. Maybe there's some wind or something blowing on the building. And so there's some sort of reactionary force at the base of the building to balance out that force due to the wind. And so the torques are, all the torques is zero, some of the forces are zero. But you know, what if those forces are acting for a really long time? What if the wind is blowing really heavy, right? Maybe it's not a hurricane, but you know, for a really tall building, it's going to catch a lot of wind, right? And so there are forces that can be kind of big in those situations. And you know, you want to make sure that the materials that the building is made of can withstand those large forces. So that's kind of the idea for the rest of this chapter, is like, how do we quantify how much force these different materials can handle? And a lot of that is empirical, right? So we have to set something up in the lab. You know, for example, we set up something with iron, right? We expose it to some forces and we see how much force we have to apply before the iron kind of deforms and changes its shape, and then replace iron with another material and then repeat the process. Just do that for a bunch of different materials, and eventually you've got some information on all the different materials. Okay, so that's the idea here for this chapter. So the starting point here, if we want to get into it, is Hooke's law. That's kind of the starting point. Hooke was the first kind of person to look into this and come up with kind of a formula that kind of describes how materials will respond to forces. We tend to look at Hooke's law in the following way. So we have some sort of spring, you know, whatever the spring is made of, could be iron or something. And that spring is maybe attached to some object with mass m. And if the spring is stretched, so suppose right here is the equilibrium position. This is x equals 0. This is the equilibrium position. Just to remind you, what does equilibrium mean? It means forces, sum up the forces, that equals 0, right? So there's no net force on this object at the equilibrium position. But this object is displaced from equilibrium by an amount delta x. Okay, and so let's try and not get too cluttered here with the black. So that means that there is a force on this object. And that force in magnitude, we can put a vector here. We can write a vector equation, is minus k, which is just some constant that has to do with the spring. times the displacement vector delta x. And delta x really is a vector. We can see that the displacement here from equilibrium is to the right. And so maybe I can draw that here. So the displacement is to the right. That means the force is to the left because of this minus sign, right? So the force is opposite to the displacement. And we've kind of already talked about this, so I'm hoping that this is sounding pretty familiar to you guys. And we call this force right here, because of this minus sign, we call it a restoring force. And if there are no other forces acting on this mass, maybe we, kind of stretched the spring a little bit and then we let go. If there are no other forces, then what's going to happen is this mass is going to come back towards equilibrium, but it's going to gain some velocity as it kind of is pulled by the force. And then since it has velocity when it reaches equilibrium, then that velocity means it has kinetic energy, right? And so it has energy at equilibrium position. So it's going to continue to move. It's going to compress the spring. And as it compresses the spring, the force on that mass due to the spring is going to change directions because the displacement will start to go this way as it moves to the left, compressing the spring. Then that means because of that minus sign there in the equation, right, then the force would be in the opposite direction. And then eventually it will compress the spring as much as it can, and then it will not have any velocity, it will not have any kinetic energy, and so then the force will push it back towards equilibrium again. And if there's no friction here, there's no other forces in this problem, this object will simply oscillate back and forth. So maybe we can write that as well. So if there's no friction, the object will oscillate back and forth. That word oscillate just means it's going to go to the right, and it's going to go back to the left, all the way back to the right, all the way back to the left, over and over and over again. And the amount of compression is going to be the same as the amount of stretching. So if you stretched it delta x and you let go, it's going to go back to equilibrium, and then it's going to keep going, and it's going to compress the spring in amount delta x. And of course, that's because of energy conservation. So it's going to oscillate back and forth in amount delta x both stretching and compressing. Right. Scroll down a little bit so there's some more space there. Okay, and we kind of calculated already like how much energy is stored inside as potential energy for a system like this. If the spring is stretched with a mass on the end there, the amount of potential energy that's going to be stored, we can just quote it here, is 1/2 k times delta x squared. Right, so the magnitude of that displacement vector delta x, and then square it. That's how much energy is stored. And what's nice about this formula, it's kind of like 1/2 mv squared, right? So looks a lot similar. So this is kind of the idea here behind Hooke's law. This is not exactly what we're doing today, but it's a good warm-up for what we're doing today. So now to kind of generalize Hooke's law, what we do is we ask, what happens to materials that are not springs, right? So springs, it's pretty obvious, like you pull on a spring, it's going to stretch, right? But if you don't have a spring, what's going to happen? Well, it turns out that actually materials that are not springs still obey Hooke's law to a certain extent. And that extent is what we'd call like the limit, like the elastic region, I think it's called in the textbook. There's like an elastic region where the behavior is linear. And we can go ahead and plot that. So notice, so I just mentioned the word linear. So notice this equation right here. The force is linear with respect to delta x, right? So the force is proportional to delta x. So that's linear, right? So materials, just any material you can think of, if you form like, let's say a rod or something like a steel rod, it's going to have a region in which we apply some force and it has a linear response, meaning that it stretches by an amount that is directly proportional to the force that you applied, which is exactly Hooke's law. But at some point here, that law is going to break down. And you guys saw this on the pre-lecture assignment, right? So let's go ahead and get some labels here. So force here and delta x. And as a matter of fact, actually the book switches away from notation of delta x and they use the notation delta L. I'll just go ahead and follow the book here, so it's closer to what you guys have already seen. And what happens is when you apply force to materials, you get kind of a region of linear behavior. So this is linear right here. That means Hooke's law. That means that that material is obeying Hooke's law. And then at some point, you have some change in behavior. It gets a little bit curvier, and maybe it does some kind of curvy kind of behavior here. This is what your book calls the plastic region. So this, I'll just refer to this as the nonlinear region. Okay? This is the nonlinear region. This thing doesn't obey Hooke's law anymore in this region here. And then somewhere over here, your book calls this point right here the elastic limit, I believe. The elastic limit, or maybe you can call it the linear limit as well. But this is the point where the material stops behaving linearly and then becomes kind of like, I don't know, it could be exponential, it could be quadratic in some way, it could, there's many different things that it could be. It's just not linear, right? So it's much more difficult to describe things that are not linear. And then at some point, this graph has to end somewhere, because no matter what material you have, if you apply a large enough force, the material is going to break, right? And so at some point, this thing is going to break, and I think the book calls this like the breaking limit or something like that. Let's just say this is, let's say material breaks. See, there's a chat here. Is this usually when you are looking into tensile strength? Yeah, we're going to get into tensile strength here in a second. Yeah, exactly. And the tensile strength is usually referring to the linear region. Yes, yeah. So for example, the elastic modulus, sometimes called like the Young's modulus, is basically telling you how this region right here behaves. So in your book, they call this They give it a letter E. It's essentially K from Hooke's law, but we call K the spring constant. This here is called the elastic modulus, or Young's modulus. Anytime you see that word modulus in physics, that usually means you're talking about a linear response of a material. So it assigns a number to the response that a material has to an applied force. So we'll see exactly that in a second, which is exactly the same as Hooke's law. So if we look at Hooke's law again, if I apply a force F, the constant that tells me how the material responds is K, the spring constant. So in essence, K is an elastic modulus for the spring. Okay, so it stretches an amount delta X when I apply a force F, and if K is really small, that means that small forces can give me pretty big stretching. If K is large, then that means I need large forces to get stretching, or to have much stretching. Okay, so where do we go from here? Well, we know that all materials are going to have this linear region. So how do we determine what that, how do we describe that region, right? Well, first of all, guaranteed, if it's linear, you can always say the force is proportional to delta L. The force is proportional to delta L. Now, how is it proportional? Well, we can always take an equation like this and we can just kind of insert some constant times delta L, right? But let's go about this in a slightly different way, okay? Let's define two quantities. And this is going to help us understand what's going on here. Okay, so there are two quantities that we wanted to define. The first one is stress, not stress from, factors in your life or whatever, but physical stress, okay, which is a force that is applied to a material over that material's cross-sectional area. Let's get a picture. So if I have some sort of maybe steel rod here like this, it's cylindrical. It doesn't matter if it's cylindrical or not, but this material here has a cross-sectional area, A, right there. And if I were to apply a force to this material, like so, then you might suspect that, okay, if the material is thinner, I might have a different response than if the material is thicker, right? And so we define this quantity stress here as force over area. And really what force over area is a kind of pressure. Okay, just to tie it into another physics thing that we're going to talk about in the future. It's actually, I think it's mentioned in this chapter as well. But that's what stress is, okay? It's a pressure on the cross section of a material. So it's the force that's applied divided by that cross-sectional area there. Okay. All right, so suppose we've applied that force to that cross-section. Well, what's going to happen is, again, every material is going to be linear for some amount of applied force, but at some point it's going to reach a limit. So we want to get an expression that describes that linearity. So we define a quantity called strain. And what strain is the change in the length of that object when the force is applied divided by the initial length of that object. So if I apply a force, that's going to tend to stretch that beam, right? So maybe I don't know, maybe it's easier to think about actually compressing the beam. But so suppose we apply some force to this steel beam here. Well, what's going to happen is we're going to get a little bit of stretching, but not much stretching. If it's like a steel beam, you have to really apply some big forces to get it to stretch. And we'll see exactly how much in a little bit. But basically, we're going to get a little bit of stretching here. So let me try and encapsulate that small bit of stretching that we're going to get. So this right here is a small little bit of delta L. And this right here is the initial length. So you can think of strain as kind of like the percentage change in length, except it's not multiplied by 100. So it's kind of like the percentage, I'll put it in quotations, percentage change in length. But notice that we're not multiplying this thing by 100%, right? So it's not exactly the percentage change in length, but if you multiply by 100%, then you would have the percentage change in length. And this strain is always going to be small for your everyday materials. You really need to apply a lot of force in order to like kind of deform objects, right? Unless you have like paper or something, maybe it doesn't take much force to deform paper, right? You can tear paper pretty easily. But yeah, so stress and strain. Any questions at this point? I'm looking at the chat here. You can give me a thumbs up if we're good to go. Stress is the pressure that's being applied to that material on its cross section, so force divided by area. Actually, let me add something real quick. And this actually, I don't think is talked about in your guys' book, but it actually is kind of an important point here. If the force is not perpendicular here, if the force is not perpendicular, then things change a little bit. We have to put the perpendicular force here. So maybe we should add that into our notes just as a little side note. If there's a force that's not perpendicular, then that's shear stress. Okay, this one, so maybe I should write that as well. So this is going to be tensile stress. This is going to be tensile stress. And we're also going to see in a little bit, we'll take a look maybe at shear stress as well. Okay. All right. And so also this would be tensile strain. Just to dot all the I's and cross the T's here. Okay, so the next thing to do then, if you have a stress on a system, then you're going to strain the system. Okay, so let's write that down. So this is important for the logic that's going to follow from here. So we're going to make some bullet points here. So, well, really, I think it's only one bullet point. Okay, so when we apply a stress, the material will experience a strain. Okay, let's put some of these things, let's bold the important things here that we're saying. So we apply a stress and the material is strained, right? So it's like, think about real life, right? When you're under a lot of stress, that means you're being strained, right? So it's very human in that sense. Okay, so that's the important thing here. We apply a stress and we get a strain. And I'm going to have to, let me zoom out for a second. I forgot to drag this down. So we'll drag that down there. We'll zoom back in. There it is. Give you a couple more seconds to write that down. Okay. We apply a stress, the material is strained. All right. Now notice here that the amount of force we apply, that's kind of the variable, right? That's kind of the variable. We can change the amount of force that we apply, but if we have a material, then this is constant, right? We have some steel column or something. Well, this cross-sectional area is fixed. This is a constant, right? Okay, and we look at this one, we say, okay, delta L, that's kind of like the thing that we're interested in, right? We want to know how much our material stretches. Well, if we know what our material is, then L0 is a constant, right? L0 is constant. We've got this steel column. We know its length. We know its cross-sectional area, right? What we don't know is the force and the delta L. So we're going to form the quantity now. We're going to take the ratio. So we are going to have another bullet point, but I'm going to write this one by hand. Take ratio stress over strain. Okay, we're going to form this ratio of stress over strain, and we're going to set it equal to some constant. Why are we setting it equal to a constant? That's kind of bizarre, right? Well, remember, we're saying that we have this linear behavior, right? Certainly this would not be true if we didn't have linear behavior, but because we have linear behavior for every material up to a certain point, then this is going to be valid. So don't try to apply this if you're looking at the plastic region, right? If you're dealing with plastics, you don't want to use this kind of idea of stress over strain equals constant. It's not going to be constant. But if you're looking at steel beams, concrete, brick walls and things, then this is going to apply, right? Or if you're looking at springs, okay? And that constant, we call this the elastic modulus, but let's go ahead and write that out. So E is stress over strain. And E over here is the elastic modulus. Okay. And stress is force over area. And strain is change in length over the initial length. Give you guys some time to copy that down. Give me a thumbs up when you're ready. I'm still waiting on a couple of you. Sammy, Matthew, Kevin, Leanne. Okay, good. Okay, maybe that was everyone. Okay, so let's go ahead and now organize the equation a little bit, and we'll see that we have F times L0 divided by another. Actually, let's put the L0 on the other side. So L0, F over delta L. We have L0 on top, and we have A on the bottom. Right? So this is our equation here, and it tells us how much materials respond to stresses. Okay, so this is how we define the elastic modulus. Now, what we can do is we can start taking a look at some values for the elastic modulus from a table. I'll just give a couple of them so we just have an idea of what the numbers are here. The elastic modulus has units of Newton per meter squared, again, the same as pressure. So the elastic modulus here has units of newtons. Mouse is giving me some trouble here. Newton per meter squared for the units. Let's go ahead and take a look here at some values. So steel, one we'll be looking at in an example problem here in a second. The elastic modulus is, the book gives it as 200 times 10 to the 9. Why don't we just write that as 2 times 10 to the 11 Newton per meter squared. So very, very large. What does that mean? It means you really need a big force to get some stretching out of steel. You really need big forces, which makes sense, right? That's kind of what we use steel for. Let's take a look at some other ones like concrete. Also, we use concrete for roads and buildings and bridges and things, right? Kind of important. Concrete does not have such a large elastic modulus. I'll stop writing the units and the E from here. So concrete is 2 times 10 to the 10. It's about 10 times less tensile strength than steel, right? Okay, how about another one? Let's go with brick, right? So how about brick? We use brick for a lot of older buildings, walls and things. How strong is it? Brick is 14 or 1.4 times 10 to the 10. Okay, so there's a couple examples. Now, one interesting thing that, and maybe you might have even thought of this before I say it, is that some materials will actually respond differently whether you're compressing them or stretching them. So just quickly, let me write that out. So when something is in compression, compression is when you apply forces like this. So these are your applied forces. So this is compression. Not to be confused with the normal force, the reaction force, which would be in the opposite direction. And also tension. Tension is when you're trying to stretch something, right? When something is in tension. That would be kind of the same picture, but the forces are in the opposite direction. Again, these are the applied forces, not the reactionary forces in the material, which again would be in the opposite direction. So compression is when you're trying to squish something down, right? Tension is when you're trying to stretch it out. And some materials will actually respond differently if you're trying to compress them or if you're putting them in tension. Wood is a good example of that, okay? Wood tends to be pretty good in tension and pretty bad in compression. Okay, I see there's some chats here. Are Young's modulus and elastic modulus the same thing? Yes, they are. Yes, they are. Oh yeah, okay, that question was already answered. Okay, yeah. All right. Let's go ahead and get into, actually there was one more thing I wanted to do. So we defined the elastic modulus. Let's rearrange the equation now. And then I've been talking for a while. I want to get into some examples. So let's rearrange the equation. So let's put the elastic modulus there. And the elastic modulus is equal to L0 over A, F over delta L. Let's move all the stuff to the other side. So let's have F is equal to A over L0 times E, right? And then there's this delta L here, okay? And this is basically Hooke's law, if you just look at this thing, right? Excuse me. It's basically Hooke's law where this thing right here can be thought of kind of like the spring constant, right? So this is constant. And so this is our linear behavior right here. This is our linear behavior. So if I were to ask you on a test, I plot F versus delta L, right? And I give you this, and I tell you this point here, and I tell you this point here, right? If you're to calculate the slope of this line, the slope of the line here, slope, is A E over L0, right? That's the slope of that line there. Okay? All right, let's do an example now. I've been talking for like half an hour, almost 40 minutes. Probably should have done an example. Let's do an example here from the book. I'll go ahead and type it up here just to save some time. So it's tension in a piano wire. Let's unbold it now. So 1.6 meter long steel piano wire has a diameter of 0.20 centimeters. How great is the tension? Tension is a force, so that's our F. I know that might trip some people up. How great is the tension in the wire if it stretches 0.25 centimeters when tightened? Okay. Now, we're being told that it is a steel wire, so we kind of have to go look up in the table what is the tensile strength of steel, right? That's our elastic modulus for steel. I'll give that to you. That is 2 times 10 to the 11 Newton per meter squared. Okay. So go ahead and work on that one. Maybe as you guys are working, I'll kind of write some stuff there too. Remember, this is the equation we want to use right here. We want to use this equation in the box just above the question. Let me know if there are any questions here. Hopefully you guys have copied that formula down. I'm going to actually scroll down now and I'm going to prepare the next example. We'll just try and do a bunch of examples from here. There's maybe a couple more topics I can talk about, but pretty much this is what this chapter is all about here. And don't worry, I will go over this example that you guys are working on. All right, so who is done with this example here, this first example? Anybody done yet? Give me a thumbs up if you're done. Oh, wow, okay. Taking a little bit longer than I expected. Okay, let me write a little bit here. I'm probably writing stuff you already know. Area, the cross-sectional area is pi r squared, right? The radius is diameter over 2. So we're given the diameter in this problem. Of course, delta L here is given to us as well. 0.25 centimeters. Kevin has an answer now, so as you get your answers, push them in, put them into the chat and compare with your fellow classmates. Kevin, now that if you're done, maybe you can calculate the strain. Calculate the strain, calculate the stress. Okay, I'm going to write a little bit more here. This formula right here is what we need to use. AE over L0, delta L. So we have disagreement in the chat. That is good. That means you both have to check your work and see who's right. Ooh, perhaps it's Kevin who needs to double check his work. Anyone else? Anyone else almost done? Once we have this area, we plug it in here. Make sure we convert our centimeters to meters. Young's modulus is just this number I gave here, 2 times 10 to the 11. That just goes in for E. Delta L and L0. We know everything on the right side.
Wait, did you want us to find the stress as well for the first example, or was that for the second example?
You can do that for this example too, since we're kind of waiting on everyone. I'm going to go through the question right now. So I'm kind of writing out what needs to be done.
Okay, thank you.
So for the area here, we want to use pi r squared, or radius is diameter over 2, right? So as long as we do the diameter divided by 2 and we can square it in our calculator like that, we'll get the right area. Elastic modulus here, 2 times 10 to the 11. I'm just leaving the units off. We know what the units are going to come out to. As long as we convert everything to meters, right? The units on our force are going to come out to newtons. Now, delta L, that's given to us 0.0025 meters. And L0 is 1.6 meters. So if we punch that into the calculator, we're going to come out with an answer of 980 newtons. Okay, 980 newtons. Give me a thumbs up if you understood that example. Okay. For this next one, I'm going to give you some time. So go ahead and take some time to copy down this next example here. I'm going to put you guys in groups. Right, so here's the next example. Go ahead and copy that down. In this problem, we're looking to calculate 3 things, okay? So maybe we can take this a little bit further. We could say part A is to calculate the stress, right? Part B is to calculate the strain. Part C, calculate the elongation. Maybe part D, you could calculate the depression. Oh, wait a minute, that's not a quantity from physics. Let's leave that off the table for now. Anyways, so does everybody have this copied down?
Not yet.
Okay, I'm gonna start getting the break rooms ready. We're gonna go for groups of 3 this time. And these groups look fine here. I'm gonna give you guys 15 more seconds. Give me a thumbs up if you're ready. We still got 5 people copying down. Okay, maybe a little bit more time then. Just give me a thumbs up when you're done. Evelyn, Denelise, Sammy, Christine, Jew. Okay, I'm going to open up the rooms. There they are. Finish copying and then join your room. Groups of 3, talk to each other, work together. I'll be coming around. You see there's a chat here. It's steel, right? So we use, yeah, Leanne, yes, that's correct. It's steel. So the same one from last time. 2 times 10 to the 11. Did you have another question? Okay. Okay, so this is group 1. Just a quick check-in. So do we understand what the question is asking us? Leanne says hello and no one responds to her. That's sad. Kevin, Evelyn, are you 2 there? Evelyn? Kevin, do you understand what's being asked? Okay, Leanne, yes, but I'm not sure where the weight comes in, unless it doesn't need to be used for part A. So the weight here, or rather the mass, right, is given. So you calculate the weight from the mass, and that's going to be the force that goes into the stress, right? So stress is force over area, and the force is going to be the weight, since that beam is supporting that machine. Yes, Leanne, yes. So 550 kilograms times the 9.8 meters per second squared to get the weight, and then that's going to go into the force that is acting on that rod. Yes, Kevin, exactly. Evelyn, are you there? I haven't heard anything from you yet. So work together, share your ideas, share your calculations so that you can get through this. Try not to go longer than like 10 to 15 minutes on this one so we can do more. All right, I'm gonna go to the next room.
Oh,
You mean vertically?
right.
Hey, just checking in to see if we know what's going on here, what's being asked.
We kind of don't. It's probably a stupid question, but is the steel rod hanging vertically?
Yeah, so it's supporting that that machine.
Okay.
So the weight of the machine is the force that acts on the rod.
Oh, okay.
Yeah, so you do the 550 kilograms times G, right? And that'll get you your force.
Mm-hmm.
And then the force goes into the stress part. Denise, you're good on that too, or?
Yeah, I'm good.
And then
I'm
Ju,
just
how are
writing
you
it
doing?
down.
Okay. And then Ju, how are you doing? Good. So that makes sense.
So far, yeah.
All right. I'll head to the next room then if there are no other questions.
Thank you.
Yeah.
Thank you.
Hello. Do we understand what's going on here? What's being asked? Okay. Where's the confusion? Wondering how to find delta L, the elongation. So you guys are already on part C? So certainly you can use the equation E equals stress over strain. If you're looking to find the strain, that's a good equation for that, right? because E equals stress over strain is a little bit simpler than, F equals AE delta L over L0, right? So yeah, start simple to find the stress and the strain, and then go after the individual quantities like delta L later. Does that make sense? Sammy, I haven't heard from you yet. And then Matthew, did that also make sense for you as well? Okay, so then we're good. That made sense. Okay, cool. Gotta go check on the next room. There are only 3 rooms, so I'll probably be back pretty quick. I am back. Are there any questions? So it looks like we have some agreement on the answer here. That's a good sign. So how are we doing? We got part A. Cool. Evelyn, you okay? No, Evelyn, you already. So Kevin, do you have part A? E is E for steel, so it's the same 2 times 10 to the 11. This one. Okay. All right, I'll go to the next room. So I'll probably be back pretty quick because there's only 3 rooms. Okay, how are we doing?
I think I'm doing okay. We're just working on the problem separately for now. And then I think we're gonna touch base.
Are you guys sharing your answers to see if just put your answers in chat so you guys can compare.
Okay.
Annalise, how far did you get?
Um, I'm still doing areas. I'm almost done. I set it up pretty much.
Okay, well, the
I'm
area,
just plugging
you don't need to solve for it, actually. It gives it to you.
Oh,
Yeah. And then Ju, can you so where are you at?
oh yeah, it says area. Got it, got it. Okay. Then I will have the answer a lot faster.
Yeah. So we haven't gotten to sharing answers because I think we're still working on it.
Yeah. For the force is equal to the weight of the machine that's hanging from the bar. So use weight equals m times g. And then the stress is force over area. Okay, I'm going to check on the next group. I'll be back shortly.
Thanks.
Hello. How are we doing over here? We got some numbers. That's good. Do we have an answer for part A? To the -6? It definitely can't be to the -6. That would be like such a low amount of stress on the material, right? Right, so Sammy, how are you doing? You making progress on it? Almost done with part A? So kind of like the key things here are that the weight is equal to, mass times gravity, right? And then that the stress is equal to F over A. And F is just equal to that weight. The area is just given to you. It's given to you in the problem statement, so. Okay. Gonna go ahead and go to the next group. Getting back again. Any questions here? Which part are we working on? Okay, 2 on B, 1 on C. Okay, working on it. Okay, do part B first. Part B is easier to get than part C. Actually, I think you need to get part B first. So the idea for part B is once you know the stress, you know the elastic modulus as well. An elastic modulus is defined as stress over strain. So you get the strain from this equation. Then once you know what the strain is, then it's a bit easier to get delta L. Does that make sense? It's possible, yeah. Leanne, Evelyn, does that help? Does that make sense? Okay, yeah. Just it's just whatever you got for the stress in part A divided by the elastic modulus is what the strain is. Just solve that equation that I put in chat, equals stress over strain. Okay, next room. That's a bit big. If the strain was 10 to the 17, then that would be like the material stretched from here, like across the galaxy. So you check your calculator input. It's what most likely happened there, Leanne, is that when you put in some numbers, and then you push the division sign, and then you put in some more numbers, and then times 10 to something, like this. And then like the calculator interprets that as just multiply the whole thing by 10 to the 11. Just make sure that you do something like this. Oh yeah, that'll do it. Okay, so I think we know what's going on here then, yeah? So I'll go ahead and go to the next room. You can't hear me? What? Can you hear me now? I'm not muted. Uh-oh. Something wrong with your computer? Okay, anyways, I gotta go to the next group, so hopefully nothing too bad. Okay. How are we doing over here?
I think we're doing okay. I think Ju's a little confused, so just walking her through the first part. I don't know how Danielise is doing.
I was just gonna report my value for strain, but maybe it might be a calculator thing. Sometimes if I plug too many things at once, I'll get like weird numbers.
Just make sure the parentheses are in the right spot is the biggest thing.
Yeah.
What do you think Danielise for the strain?
I got 1.6 times 10 to the negative 10.
Oh, that's not what I got at all.
Maybe I did something wrong.
I have to check my work. I got 8.98 times 10 to the negative 6. So yeah, that's really different. How did you get that? If you can walk me through the process.
So I used the E equals stress divided by strain, and I just tried to like isolate strain. So I divided E by the stress. Might be a calculator thing for me.
No, I have to.
That's the correct method.
Yeah.
I did it totally different. Okay. That's probably right then. I actually went backwards. So I found the delta, the change in the length first.
Mhm.
Then I used that to find the strain. Wait a second. I'll rework it and I'll let you know.
Okay, so I think it's fine here, yeah? No questions?
I think so. I'll just have to like rework it, or I'll see what I did.
Your method is correct. You just need to make sure the calculator is doing what you want it to do.
Okay, got it.
I just wanted to check actually, is strain a unitless number because the units cancel out?
Yes.
Okay, cool.
Okay.
Yep. Good observation.
Oh, good.
Hello, how are we doing over here? Still stuck. I thought you guys figured it out on B. Elastic modulus equals stress over strain, the definition. So multiply the strain over, divide by E. Stress divided by E equals strain. You're off by a couple orders of magnitude. What did you get for your stress? Yeah, that's the correct value for the stress. Yes, that is the correct value for E. No, I don't think that's correct. It's off by 2 orders of magnitude. So 1.8 times 10 to the 8 divided by 2 times 10 to the 11. Oh, whoops. Divided by 2 times 10 to the 11. Well, I'm able to get the correct answer here. It should be times 10 to the minus 4. Oh yeah, it's times 10 to the 8. No, it is times 10 to the 8. Perhaps you forgot to convert your area to meters squared. So since you have centimeters squared, 1 centimeter squared is equal to 0.01 squared meters squared. 1 centimeter equals 0.01 meter. You have to square that conversion factor. So I think that is probably where the mistake is. Okay. Okay, I'm going to close the rooms soon. I'm going to broadcast a message here in a second, and then I'll go over the questions. Or the question. Okay, so we'll go ahead and close the rooms now. Welcome back. Wait on everyone to get back before we start. 10 more seconds, then everybody's going to be forced to be back. Were you guys able to finish it, or? Okay, everybody is back now. So we'll go ahead and go over the question, and then it's probably a good time to take like a 10-minute break or something. So that's what we'll do. We're going to go over the question. So stick around for the question. Important that we know how to do this. So stress is defined as force per unit cross-sectional area. So force over area. In this question, we have a steel rod here, 2 meters long, etc. that is supporting the weight of a 550 kilogram milling machine. So the force here is equal to the weight of that milling machine, and that weight is m times g. So 550 kilograms times 9.8 meters per second squared, right? That's going to give us units of newtons. And the answer we get for this here is 5,390. The area here is given to us as 0.30 centimeters squared. We need to convert that to meters squared though. So that's going to be 0.30 centimeters squared times 0.01 centimeter per 1 meter. Let's actually write it like this. We're used to seeing it kind of like this. Huh? So that's our conversion factor. But notice, oh, excuse me, I wrote that backwards. It should be 0.01 meters per 1 centimeter. Right? So now what we need to recognize is that if I were to just go in and do this conversion like this, I would only cancel 1 power of the centimeters. So my units would be centimeters times meters, right? So I need to make sure I square this thing to convert both of the centimeters, right? And then I'll be left with meters squared. So this is 3 times 10 to the minus 1. And this right here is 10 to the minus 2. And it's going to be squared. That's going to be 10 to the minus 4. So the number we have here is 3 times 10 to the minus 5 meters squared. Okay, you can just use your calculator for that. So the stress then is equal to the 5,390 newtons divided by the 3 times 10 to the minus 5 meters squared. And what we get for this numerical value here is 1.8 times 10 to the 8th Newton per meter squared. There is a name for units of newtons per meter squared, and that is Pascal. So sometimes you'll see Newton meter squared written as P, capital P, lowercase a for Pascal. Which is a unit that we'll actually see in the next chapter a lot more, which is a unit of pressure. Okay, so that's our answer for the stress there. How about the strain? Well, the strain is equal to, well, the elastic modulus is stress divided by strain. So stress divided by elastic modulus is going to give us the strain. Just for those of you who need to see that, elastic modulus is defined as stress divided by strain there. So we can move these two terms. We can swap their places, right? I can multiply both sides by strain, and I can divide both sides by the elastic modulus. When we do that, we have that the stress is 1.8 times 10 to the 8 Newton per meter squared. And the elastic modulus for steel is 2 times 10 to the 11 Newton per meter squared. We can see here the units cancel, giving us a unitless quantity. And this comes out to 9 times 10 to the minus 4, I believe. Yeah, that's correct. 9 times 10 to the minus 4 Newton, or excuse me, this is a unitless quantity, right? And To get part C, the elongation, that's delta L, right? So this here is the strain, and strain, oh, we're switching parts, so let's switch colors. The strain is defined as delta L divided by the initial length. Okay, so that's how we're going to find the elongation. So we take this 9 times 10 to the minus 4. We'll go ahead and write this one more time. So this is delta L over L0 is strain. We can rearrange this equation so that we have delta L equals strain times L0. And the strain is 9 times 10 to the minus 4. And L0, we read it from the question here, is 2 meters. 2 meters. And so our elongation is 1.8 times 10 to the minus 3 meters, or in other words, 1.8 millimeters. And this example really highlights the fact that because steel has such a large elastic modulus, the elastic modulus for steel, again, is 2 times 10 to the 11 Newton per meter squared. Because steel has such a large elastic modulus, even though we're supporting this very heavy machine, 550 kilograms, which comes out, it's over 1,000 pounds, right? Pounds is kind of what we're used to thinking of. We only get a stretching of this material, of this steel rod of 1.8 millimeters, so very little stretching, right? And that's good because we don't want things to stretch much. We want things to stay where we put them. We don't want them to deform. If they deform, then that's usually going to cause some problems. Okay. All right, we have a chat here. Oh, okay. Private chat or something. Okay, so I said now that we've covered that, are there any questions for me about that problem there? Give me a thumbs up if there are no questions. Thumbs up if there are no questions. Ju, Sammy, Matthew. Okay, Sammy and Ju. Any questions? Okay, Sammy is the last one. Any questions, Sammy? Okay, so let's go ahead and take a break. Let's take a 10-minute break. We'll meet back at 7. So meet back at 7:17. Okay, so go ahead, take the break. We'll come back and we'll talk about shear, and maybe we'll talk about bulk moduli, and do maybe a few more examples, and we'll see where we stand from there. Okay, so I'll see you guys in 10 minutes. Any questions for me, just put them in the chat and I can answer them during the break. All right, see you guys soon. Thumbs up if we're back. Okay, about half of us. We give like a couple more seconds here. Actually, let's go to the next, let's go up over here. Next thing we're going to do is shear stress. Okay, so here we have, let's just get a similar picture to what we had before actually. We have some sort of rod like this. Let me scoot that over a little bit. So here we have tensile stress, which is when we apply a force like this to some cross section. Okay. And this thing elongates a little bit. Oh, whoops. By an amount delta L due to that tensile stress, where the force is perpendicular to that area there. Of course, if there's a force applied on this side, there must also be a force applied on this side. There's got to be some sort of balance of forces here because this thing isn't accelerating. It's just elongating. Once it elongates a certain amount, then the net force on it will be zero. While it's elongating, the process of it actually elongating, the net force may not be zero because the center of mass is moving, right? This is tensile stress. What if we have a situation where we have something like this, where we have kind of like this similar thing going on with this rod here, but instead of applying the forces like that, we have the forces being applied like this in the plane of that cross section there. So these are equal and opposite forces again. Well, in this case, what's going to happen is this thing is going to not necessarily elongate, but it's going to kind of tilt on its side, right? It's kind of, it's going to do something like this, right? It's kind of going to elongate kind of in the like perpendicular direction, right? So it's a little bit maybe hard to describe that in words. But we can still measure an amount of elongation here, delta L. Let me go ahead and move that force. This is not a product of the force and delta L, but that's just the amount of elongation there. And if we have that, we call this shear stress. So this is shear stress, where the force is in the plane of the area, okay? The book gives kind of a nice little example here. So speaking of books, if you have a book like this, right? Book looks something like this, and you have all these pages in here, right? This is like all the pages, right? And you stick your hand on top of the book like so. Let's try to draw that better. So you stick your hand on the book like this, and then you push on the book in this direction. What's going to happen to the book? Well, first off, if you push on the book in that direction, down here, there's going to be some friction force or something that's going to push on the book in this direction. And what's going to happen is the book is going to, it's going to do something like this. We've all seen this, right? You push on a book like this, and here's the pages again. And it kind of tilts over, right? And this is your delta L right here. Okay. And the way we describe that amount of kind of shear elongation is the following. Very similar to what we've seen before. The book presents this equation here. force over area. So this is the stress part. And then this is the initial length here. Now this is the formula that the book just presents, but we can do a little bit better than that. We can again say that, okay, the shear modulus, which we call G, this is the shear modulus, again is equal to stress over strain, but this time it's shear stress over shear strain. And we could go back and modify our previous equation if we want to, and we could say tensile stress divided by tensile strain. This is good enough for now though. So shear stress over shear strain, and the shear stress is equal to that force over the area, and the shear strain is equal to the delta L, the shear kind of elongation over the initial shear length. Now, this is where it gets a little bit maybe tricky. The shear strain here, the delta L I labeled in the diagram, it's this amount right here. Let me highlight it in, let's go blue here. So this is the amount of delta L there, but the L0 is still this length here, okay? And you can kind of understand why. If you have a really long material and you put some shear on it, you would expect more, you would expect that delta L to be able to be larger. And the reason for that is because obviously if you have a really tall, let me get a picture here. If you have a really tall rod like this, right? Really tall rod like this, and I put some shear stress on it, then there's more material. There's more material for this thing to elongate in that direction, right? So your delta L would be larger. Your delta L would be like this much. Okay, so more material, it's easier to elongate that material in that direction. Okay, and so we see that when we take the ratio of shear stress over shear strain. Notice in this equation here, and now I'm highlighting in purple, that L0 here is in the numerator, not in the denominator. In the strain over here, it's in the denominator, right? But when we're looking at actually calculating delta L, it's in the numerator. And just like for the other equation, it was the same for the other equation as well. Delta L for tensile stress and strain. Okay, so that is shear. So there's one other thing that we can do here before we go into like some examples. We've got tensile stress and strain. We've got shear stress and strain. We've got the elastic modulus. We've got the shear modulus. What if you have like fluids, right? What if you have, like some air in a balloon, right? And you're blowing into the balloon. How can you describe that increase in volume in the balloon due to your blowing, right? You blow the air in, you increase the pressure, right? Inside the balloon, you're trying to add more air in there. But then the balloon expands and then the pressure inside matches the pressure outside, the atmospheric pressure, the pressure from the air. A way to put it in the physics language that we've seen so far, we haven't really talked about pressure, air pressure yet, would be to say that the forces on the inside due to you adding in the extra air is going to be equal to the forces from the outside that the air is pushing on it from the outside. Once that balances out, then that balloon has stretched to the amount that it's going to stretch. So we can describe that too, and that's called bulk modulus. Okay, and bulk modulus, again, the symbol here for bulk modulus is B. So this is bulk modulus. And this describes volume changes. Volume changes. So bulk modulus, and the book again just presents the formula here. Delta P, minus delta P over delta V over V0, like so. And now it's very crucial here that we talk about pressure, okay? So this is a change in, not pressure, but a change in pressure. And it's very important that we put the delta in here because, and we'll talk more about this in the next chapter, there really is this thing called air pressure, and all the air around us is really pushing on us with actually substantially large forces. And you have to go above that pressure if you want to increase the volume, let's say in a balloon. But let's say maybe you have a balloon, blown up already, and maybe you take that balloon into an area where the pressure is lower. What's going to happen to the volume of the balloon, right? Well, if you take the balloon into an area where the volume is less, so then the balloon is going to expand. So this is change in pressure here. By the way, I hope that even though, maybe in chemistry you've seen something like ideal gas law, right? Well, we don't need the ideal gas law actually to describe something like that, like a change in volume. We can use something like this, bulk modulus. So that's kind of an interesting thing, right? So we don't necessarily need ideal gas law. As a matter of fact, this works for fluids as well. So a lot of fluids are incompressible, like water, for example. You apply a very large pressure to some water, and its volume doesn't change very much, but its volume does change according to this linear relationship here that we're developing in this chapter, right? It just changes very little. Okay, so change in pressure up top. The change in pressure, this is the bulk stress. So bulk stress is a change in pressure, okay? And on bottom, we have bulk strain. So this is the kind of elongation, but it's really a volume, right? So it's like a change in volume over the initial volume. So the volume elongation, maybe you could call it. And that is bulk strain, okay? So that is a bulk stress over bulk strain. The minus sign there is to indicate that if there is a positive change in the pressure, then the volume of the object or the system in question will decrease. So let's get a picture to go with that. So suppose I have, like a some sort of fluid here in a container. Maybe it's like water or something. Maybe I should use blue. Okay. And we apply some pressure from the outside of this fluid. It could be in a container, and it may not actually be in a container. But here it is. We have applied some force on the outside, and I didn't mean to make that one extra long or anything. So let's decrease the size there on that one. Okay. And so these forces here, these are all forces acting on this body here. And the force over the area is equal to the pressure here. Okay. Now, if this represents an increase in pressure, so if the pressure is increased, what's going to happen to the size of that ball there of fluid? If pressure is increased, what's going to happen to the size there? Well, all the forces are pushing it inward, right? So it's going to get compressed. Its volume is going to decrease. So the pressure is increased, the volume will decrease. Now you could maybe think about, maybe a balloon again. If you were to blow up a balloon, right, so that it fits in your hands, so you could just kind of grab the balloon. Let me go ahead and switch to the full screen here. I'm going to stop sharing for a second so you guys can see me. If you were to just blow up a balloon in your hand like this and just kind of just crunch down on it and compress it, right, you're increasing all of the force on the outside of that balloon and you're going to crush it down, right? And if you push so hard, probably at some point you might pop the balloon, right? But the balloon is going to pop because you didn't push equally on all sides. If you could push equally on all sides, you really would just decrease the volume. So you maybe give that a try yourself. If you use a small balloon that you can kind of fit in your hands and compress it a little bit, it'd be something interesting to try. So I'll go ahead and share the screen again. So this whole idea, these ideas of shear stress and shear modulus, shear strain, bulk modulus, bulk stress, bulk strain, it's really the same concept, right? And so I hope you guys are comfortable that I'm kind of introducing all of that all at the same time. So let me go ahead and summarize now everything we've just done basically today. So let's go ahead and get a clean slate here. So we have some kind of modulus is equal to some kind of stress over some kind of strain. And that really is what encapsulates everything for this kind of second half of this chapter. And the modulus is something that's constant because we're in the linear region. Stress is something like, force over area or pressure. And then strain is something like delta L over L0 or delta V over V0, something like that. Okay, so that's the idea here for this second chapter. Let's say take a look at an example, maybe using one of these other moduli. And so I have to, again, kind of pull an example from another textbook because your guys' book doesn't actually have examples for shear or bulk. So I'll go ahead and pull an example from another book here on bulk stress and bulk strain, so we can get some practice with that. Whoops. Get some space there. So I'm going to put this right here. Let's take the bold off. A hydraulic press contains 0.25 cubic meters of oil. Find the decrease in volume of the oil when it is subjected to a pressure increase of 1.6 times 10 to the 7, and then these units of Pascal, which is really just Newton per meter squared. Okay. For those of you who are interested, Pascal is maybe not the unit of pressure you're used to thinking. You're probably thinking in terms of PSI, which is pounds per square inch. When you go to air up your car tires, you're trying to get them to a gauge pressure of 36 PSI, 36 pounds per square inch. And what do I mean by gauge pressure? I mean that's in addition to the atmospheric pressure, which is about 14.5 PSI. Okay, so in terms of absolute pressure, your car tire is around 50 PSI. Okay, the bulk modulus for oil is B equals 5.0 times 10 to the 9 pascals. And it's, okay, we don't actually need that information. Okay. Right, so we won't actually need that extra bit of information they're trying to give us there. Okay, so here's the question. We have a hydraulic press contains some amount of oil. Find the decrease in volume of the oil when it is subjected to a pressure increase of this amount. The bulk modulus for oil is given. We'll talk more about hydraulic presses actually in the next chapter when we discuss fluids. Okay. So I'll go ahead and leave the image here as is with this equation up here. So if you want to do bulk modulus, right, just put B here. The bulk stress is the change in pressure, delta P, and the bulk strain would be delta V over V0. And then of course it will be a volume decrease, so there's a minus sign there. You can maybe write that out, bulk modulus. Okay, and do you guys want to be put in groups or do you want to work solo? Give me a thumbs up if you want to work in groups. Thumbs up if you want to work in groups. Nobody gives a thumbs up. Okay. All right, so we'll just work this one solo then. I don't know why people don't like to work in groups. It's much better for you to take advantage of the fact that you can share your work with others. You actually learn better. But go ahead, I'll give you guys 5 minutes to work on this one. I'm gonna go ahead and turn off my video so I can eat a little bit. You guys can still hear me, so if you have a question, I can still answer your question. Does anybody else have the answers yet? Only a few people have given answers. We'll give it a couple more minutes, I guess. You just want to solve that equation for delta V, the bulk modulus equation. Those of you who are done, go ahead and calculate the bulk strain, delta V over V0, with the minus sign. Okay, I'm gonna give about another 60 seconds and then we're gonna go over it, okay? I'll go ahead and set up a shear stress example as well. So that way we at least have one example for each type. Let me scroll down here. So keep working on that example. I'm going to get another example ready. Lots of examples, right? More practice, more better. The minus sign isn't super important if you understand that the volume is decreasing. If you understand the volume has to decrease if you increase the pressure on the outside, and you know that it's going to decrease the volume, then the minus sign is not that important. But if you're actually analyzing equations and things, it gets important to carry the minus sign excuse me, with you. Let me give some space. And then I have to write in delta L here. Get a picture for this next part. Okay. I'm sorry, I scrolled down and I blocked the question out. I don't know if... Okay, let's go ahead and go over this first example here. The first example is a hydraulic press. Here contains some oil. Find the decrease in volume of the oil when it is subject to a pressure increase of 1.6 times 10 to the 7 pascals. We're given, the bulk modulus. Okay, so we can use the bulk modulus equation. B equals minus delta P over delta V over V0. And we can solve for delta V. We can solve for delta V by just moving the delta V over to the other side. So leave the minus sign where it is. We're going to have to divide by the bulk modulus. And what we're left with is delta P it's delta P times V0, because V0 is dividing in the denominator here. So the V0 will flip up and multiply. So multiply delta V over, divide B over. So this is the equation that we want right here for this problem. So we just plug in numbers. So minus 1 over 5 times 10 to the 9. I'll just leave the units out for this one. Delta P was 1.6 times 10 to the 7. 1.6 times 10 to the 7 is about 100 times the atmospheric pressure. Just to give you a sense of how much pressure that is, that's a lot of pressure. And it makes sense because hydraulic presses are used to lift cars and other heavy things. Okay, so delta P is this value here, and V0 is 0.25 cubic meters, so we don't need to convert that. All right, what do we get when we crunch the numbers here on this? We get minus, and I believe the people who put their answers in the chat were correct on this one, minus 8.0 times 10 to the minus 4. And that is meters cubed there for the units. We'll box this in orange here. Halloween is right around the corner, right? Okay, so any questions about that? Any questions about that one? Okay, so the second thing that I asked, since it was asked in the chat, what was the second thing I asked the student who already finished what I want them to do, just so they'd have something extra to do, is just calculate delta V over V0. And if you calculate delta V over V0, you get minus 0.0032, or a change of roughly minus 0.32%. So a very small decrease in volume. Okay, very small decrease in volume. All right, so that completes the bulk stress and strain example. And now I got another example for you guys. Again, it's from another book, but that's good because the book we have doesn't have an example of it. So let's get an example of it here. We have a brass plate is subject to shear forces, as shown in the figure on the right there. The plate is 0.8 meter square, which means, by the way, this diagram is meant to be like 3-dimensional here. So it's meant to look kind of like this. It's like a 3-dimensional thing here. That means that the side here is 0.8 meters and the side here is 0.8 meters. Okay, and this height right here, which we call L0, that's the thickness of 0.5 centimeters. Okay, so it's not drawn to scale here by any stretch of the imagination, right? So that's the task. Calculate the calculate the force exerted on each of its edges. If the resulting displacement there, delta L, is 0.16 millimeters. Okay, so I'll give you guys like 5 minutes to work on that. Just remind you again that if we're dealing with shear modulus, which the book uses the letter G for that, that's going to be shear stress over shear strain. Right? And shear stress is force over area, and shear strain is delta L over L0. And this is the same as L0 for tensile stress. Sorry, tensile strain. And this delta L is now like a sideways change. Or, well, I guess we should be more, I should use language. So this is parallel to the force, to the shear force. So it's kind of like sideways, the sideways delta L in this diagram that we've drawn here. But it is the delta L in the parallel direction with the force. Any questions about that one, or we're good to get started there? Give me a thumbs up if we're good. Couple more people. Just go ahead and start working on it if you're ready, and then just let me know if there's a question here. We'll go over this one too here in like, say like 5 minutes. I'll give you about 5 minutes to work on it. Actually, you know what? On this one, since I let you guys choose last time, if you want to do it solo, I'll go ahead and put you guys in groups this time. So let's see here. Okay, here we go. So go ahead and join the room. So you'll work in groups this time. Finish copying the problem down before you join your group, okay? Join your breakout rooms, Matthew, Kevin, Leanne. Join your breakout rooms, please. Okay, just let me know if we understand what's being asked. So any questions about what's being asked?
I don't think so.
Okay, Leanne says where to start. Okay, you start with the equation that I kind of wrote down here. So let me share the screen again. So this comes from the definition of the shear modulus here. Any modulus, in fact, any modulus is stress over strain. Okay, so if we're solving for the shear forces, right, what is the force exerted on each of its edges? And that's what we're looking for. We're looking for this force F. Right, so we want to solve that equation for F. So G equals F over A, parentheses, divided by delta L over L0 in parentheses. So just solve that for F. That's the starting point right there. Does that make sense? I just don't know what values to use for the variables other than delta L. Okay, so let's start with maybe the area here. So the area is the area that the force is being applied at. So this, let me highlight it in maybe purple. So the area of this piece up here at the top and the area down here at the bottom, of course, they're assumed to be the same area, right? And that area is just given by the 0.8 meters squared, right? So it's just side times side, right? Since it's like a rectangle, but it's actually a square in this problem, but yeah, so 0.8 meters squared for the area. Now L0 is the thickness piece here, the 0.5 centimeters. So this here is L0. So you've used up all the dimensions there of the material. So you've used the cross-sectional area. What's left is the thickness. That's going to be your L0. Does that make sense? So that's just something that you probably, you kind of have to just memorize. So when you're dealing with tensile stress and strain, for the case of the tensile, that's when you have a force like this and it's perpendicular, then this right here is L0. It's kind of the same for shear. So now this is F parallel, and it's still L0 here. That one is still L0. I need to see it once, and then I can just try to mimic it for future problems. Yeah, just just keep trying things. If you're not sure what to do, just try something, and then just kind of try and identify your mistakes when you think something has gone wrong. How's so is this good for you for now? And then also Sammy, I don't know if I heard anything from you. Okay, I'm gonna go ahead and go to the next group then. So good luck on that. Hello, do we know what's going on here? Do we understand what's going on? Actually, no, it wasn't. Good point. I completely forgot to give that. So that is 7 times 10 to the 6 pascals. Let me go give that to the previous group since I forgot. I forgot to give the shear modulus for brass, so let me go ahead and give that to you there. That's the shear modulus for brass. How are we doing over here? Are we good? There's one thing I forgot to give everyone, and that's the shear modulus for brass. So I just sent that in the chat for you guys.
Okay.
Are there any questions here?
So we have to find the initial length, or L0.
Use that 0.5 centimeters that I gave in the figure there.
Oh, okay. So that is L0. Got it.
Mm-hmm.
Okay. That makes a lot more sense now. Okay. And then just to be clear, the 0.3 meters squared is the area given, right?
0.3 meters squared. There's no 0.3 meters squared given.
Oh.
What are you talking about? 0.8.
Oh, okay, yeah, I did write it down wrong.
You have to square it, though. You have to square it. So it's 0.8 meters on each side of a square.
Okay.
So
Got
you
it.
square that one. Any other questions? Matthew, you?
So 0.3. Okay. Oh, so 0.8 meters squared.
Yeah, so square the 0.8, so you get 0.64.
Got it. Okay. I think I wrote it down wrong. I think I put 0.3, so I was confused. Okay. I think I'm good from here. Just plug in everything.
Okay. Matthew, I haven't heard from you yet.
First.
Oh, sorry. Matthew, I haven't heard from you yet. Okay. All right. I'll be back around. Okay. How are we doing now? Have we made some progress?
I actually did the problem. I don't know if it's right, but I think that Leanne's still a little confused. So I think I'm just trying to see where she's at. But at the same time, I don't know if I did it right.
Yeah, I'm not sure what the force is either, because that is exactly what we're solving for, right? So, right. So we need to make sure that we solve for it, and then we'll know what it is. So that's why I said, I think last time I shared the screen here. Let me just pull it up again. So we're solving this equation right here for F. So solve this equation, G equals F over A divided by delta L over L0. L0 is your 0.5 centimeters. You should convert that to meters. A is 0.8 meters squared, right? Delta L is the 0.16 millimeters. We want to make sure we get all these quantities in terms of meters, right? When we finally plug everything in. Okay, let me read your messages here. It wouldn't matter necessarily what letter you use for it, right? As long as you plug in the right numerical value. So we use G for the shear modulus, B for the bulk modulus, and E for the elastic modulus, or sometimes called the Young's modulus. So G in this problem was what I gave earlier. So 7 times 10 to the 6 pascals, or Newton per meter squared.
Can you actually, oh, I'm sorry, I didn't realize I was unmuted. Can you explain again why the initial length is that vertical part? I don't think I understand why you would choose that instead of Like, why don't we use like the Pythagorean theorem to find out what the change of L is instead of
Right.
like
When you actually calculate the numbers, you understand why. So delta L is very, very small compared to L0.
uh-huh.
So in reality, we have something like this where it looks like this, and then there's some shear force on it, like this,
Mhm.
and then it virtually looks the same. It's just like slightly slanted. This is slightly exaggerated here,
Mhm.
but if we were to draw the triangle, this would be L0, or sorry, delta L.
Mhm.
This would be L0. And then this maybe would be like, let's call it like capital L or something. And capital L squared would be L0 squared
Mhm.
plus delta L squared. And if delta L is small compared to L0, then delta L squared is even smaller, right? So let's say L0 is 1 meter. And let's say delta L is like 10 to the minus 3 meters, or in other words, like a millimeter.
Mhm.
Then delta L squared would be equal to times 10 to the minus 6, right?
Mhm.
So on the right hand side here, we have something which is 1.000001,
Mhm.
basically 1, right?
Yeah.
So when I take the square root on both sides, L is approximately L0. Oops, L0. So in reality, it doesn't matter whether you use the Pythagorean, like the length along the hypotenuse, or the L0. It's the same regardless. And since we're working in the region where the material is linear, it has a linear response to stresses, L0 or this hypotenuse length are the same pretty much always to first order approximation. So that's why it's basically the same, because delta L's are always going to be small. Your bulk moduli, your shear moduli, and your elastic moduli are all very large numbers, and so delta L is always going to be small unless you start deforming the material. When you start deforming the material, then maybe we need to be more careful. That's pretty much it.
Okay. Gotcha. Thank you. That was really helpful.
Welcome. Okay, that makes sense. I just assumed it was, so the formula would be A over delta L over L0 G. Leanne, maybe one way to make it a little bit easier to solve would be if G equals F over A, and then flip and multiply the other one like this, right? And then since you're solving for F, you just want to move everything to the other side. So G, A, delta L divided by L0. Right, so we still can use, like, the rules from algebra, right? If we're dividing by a fraction, just flip and multiply it if that makes it a little bit easier. So I don't know if this formula is the same as what you got, but there it is.
Wait. Wouldn't I'm so sorry to interrupt. Um, wouldn't the delta L, I'm sorry, the initial length or the initial L be 0.8? Because I know you drew the diagram where,
The way that I drew it is it's going to end up being the 0.5 centimeters.
okay, if we were reading the question though, say you gave us this like question on the exam, if it says like the plate is a 0.8 meters square,
Mhm.
is this how we should draw the diagram?
It depends. So it depends. So actually, in the book that I got the question from, that is exactly what it wants you to do. So it does, in fact, talk about a plate where um, it's square. Let me see if I draw this correctly. So it's square on, I believe it's square like this, and then it's thick like this. And there are shear forces here, but I just changed it because it's just, I think it's easier to understand if it says it's 0.8 meters square than just put the shear force on the other side so the area is easier to understand what to do.
Okay.
I did change the example from what I had in the book, which it is kind of like what you're saying.
Okay.
But yeah, in this case here, then you would have like this would be 0.8 meters, and then the area on, whoops, not that face, but the area on this face here, or this face here, would then be 0.8 times the thickness, what was it,
Wait.
0.5 or something,
Yeah.
centimeters.
Okay.
Yeah,
Alright.
0.5, yeah.
Okay. Thank you.
Yeah. All right, everything makes sense, Leanne? Sammy, how about you? I'm going to assume that is perfect sense. Leanne, how are you doing? Are you good? Okay, thumbs up, I see it. All right, I'm going to go to the next group. Hello, how are we doing over here? We all got the same answer. Okay, that's good to know. So I'm going to close the groups probably in about a minute after I check up on the next group. How are we doing over here?
Um, we're throwing out some answers. I got 2.6 times 10 to the 6. And I think Ju got 1.4 times 10 to the 8. So we're trying to figure out.
A little bit of disagreement, okay.
I can
How
type
about
them in.
Matthew? How about Matthew? What did you get?
I think he might be still working on it.
Okay, I am going to close the rooms here shortly in about a minute. I'll broadcast out a message. So
Okay.
just keep working until the rooms close, and I'll go over the question.
Okay.
Welcome back. We'll wait until everybody gets here. We'll go ahead and go over the question. I'll go ahead and clean up some of the stuff I've written here already, so we have a nice clean slate here. Go ahead and share that now. Okay, so in order to get the force here, we have to solve for the force from the equation for the bulk modulus, okay? So, or, excuse me, shear modulus. So we use the letter G for shear modulus, and of course that's going to be a stress over a strain, okay? And the stress here is going to be the force over the area divided by the change in the length there divided by L0. And the way we've set the problem up here, kind of have to be careful about what we mean by these different distances and stuff. That's why I gave a diagram here. So the bottom face, let's get a more accurate diagram actually. Since this one doesn't even look square, but we're saying that this thing is square on the bottom here. So this looks a lot more, well, not quite. Okay, this looks a lot more square. So not quite to scale, but this length here I said was 0.5 centimeters. So not quite to scale, right? That would ultimately be much smaller than these 0.8 meter square faces here. And then we have our forces like this, our shear forces. And so hopefully it's clear that our L0 here is going to be 0.5 centimeters. And the area here is going to be 0.8 meters quantity squared there. Area of a square, side times side, right? Or side squared. All right, so we want to solve this equation for F. All we have to do is multiply everything to the other side. So G times delta L over L0, and then multiply the A over as well. So it looks like this. That is equal to that shear force. Now we can plug everything in. I did have to give you guys the shear modulus for brass. I believe it was, I can't remember off the top of my head, was it 7.0 times 10 to the 9 pascals? Is that the correct value there? Delta L was given as 0.16 times 10 to the minus 3 to convert it to meters. Somebody let me know if this is the correct shear modulus. So I typed it in chat for everybody. Maybe I can just scroll back up. Go ahead.
10 to the 6 for our chat.
Okay, yeah, I see that. Yeah, 10 to the 6. Not 9. I drew my 6 upside down on accident. Okay, and then the area, 0.8 meters, and we quantity square that. Divide by L0, which is 0.05, excuse me, 0.0. Let's just convert it. So 0.5 times 10 to the minus 2. And that's going to be meters there. When we crunch all these numbers here, I'll just plug it into Wolfram Alpha. So 7 times 10 to the 6 times 0.16 times 10 to the negative 3 times 0.8 squared divided by, and then whenever I push the division sign, I always open up a new set of parentheses just to make sure I don't mess up my order of magnitude. And then what I end up with here, and let me just double check here, I got parentheses in all the right spots. What I end up with is 1 point, oh, whoops, did I make a syntax error?
Is the decimal point off for you?
Oh, I think I made a syntax error because it didn't interpret my calculation. It just like read back a number.
Oh.
I'm wondering why it's doing that. .00. Let's try that. Oh, there it is. I see it. Okay, there we go. I was like, I don't see anything. I had a random multiplication symbol in there somewhere. So 1.43 times 10 to the 5th newtons. Okay, so let me know if that is what you got there for that answer. Give me a thumbs up if that's what you got. Did nobody get the same answer? So what were the answers that other people were getting here? Let me scroll back up. I saw some people put answers in the chat. Only one person, 4.48 newtons. Seems quite a bit. Seems significantly low. 1.4 times 10 to the 8. Did we convert our units properly? We're off by orders of magnitude here. Let's go ahead and check our calculations here. So 7 times 10 to the 6 times 0.16 millimeters. So times 10 to the minus 3. So that part is correct. And then we have, we have 0.8 meters squared. Got that part. And then divided by half a centimeter. So that's like 5 millimeters. So this is going to be 0.005. So this is correct here in my calculator here. It should be times 10 to the 5th. And so you just need to check your calculators on that because it's probably just a calculator error. If you have the correct number in front, usually what I see the mistake from what I see as the mistake from students is usually involves a number in the denominator somewhere, especially when there's a factor of 10 that needs to be multiplied by. That order of magnitude, sometimes students forget to put that thing in parentheses, and then it ends up multiplying their answer at the end instead of dividing it. So you have to be, well, Evelyn, that would be volume, right? Length times width times height would be volume. Okay, so any other questions on that one? Yes, only the area in the plane where the force is parallel. Yeah, cube, not square, right? So it is the area of this cube right here. Let me go ahead and highlight it. So it is that area right there. It's the same area that we used for the elastic modulus. So it's the area at the top. So we can go ahead and maybe draw another picture here. Let's draw another picture here. So when we're looking at elastic modulus, maybe we had a cylinder like this, and it was this area here, right? And we had a perpendicular force, right? And so when we're talking about shear, shear looks like this. It's the same area there, but the force is now parallel to that area. Okay, so it's the same area. And in fact, it's also the same L0. So this is L0. This is also L0. The difference is in this case, you have delta L in this direction. And in this case, we have delta L is this bit right here. Like that. So that's the difference between the tensile strain and the the shear strain. Okay, any questions about that? For the next 20 minutes, the last bit of the class here, what we're going to talk about is one of the kind of final sections in the textbook. It's called fracture. That was another diagram I drew for one of the students. So, okay, so let's talk about fracture. Fracture is when a material buckles, it breaks. So this is like breaking or breakdown of materials. Okay. And when we talk about breakdown of materials, usually we want to understand two things. We want to understand, okay, how much stress can I put on the material to make it break? And also, how much stress, like what's the safe amount of stress I can put on the material where, you know, over a long period of time, right? If I build a building over a long period of time, the material might weaken due to some factors, right? You know, for example, an old building or something might have some rust on some support beams or something, right? So there's wear and tear, right? So how much stress can I put on a material before it breaks, it actually breaks? And then kind of what is a safe amount of stress to put on something where I can have that much stress on it for a long period of time and nothing bad is going to happen. Nobody's going to die because the building collapses or something, right? Or a bridge like breaks and people fall into the water or something. So we want to avoid disaster. So that's the idea here. So the first thing we'll take a look at here is a table from the book, and they call this the ultimate strength of materials. Okay, and we'll just quote a couple of them here. It's in the book, and it's in section 9.6, chapter 9, section 6. So we'll take a look. Maybe here's steel. We've been working with steel a lot. The book gives, actually, let's move this down a little bit. The book gives actually the ultimate strength in terms of the elastic, the tensile, and compressive strength. So tension and compression, and then shear strength as well. So let's go ahead and break it down for each one here. So tensile, again, tensile means when it's in tension. So you can, a lot of materials kind of behave the same, like metals tend to behave the same, whether they're in tension or compression. But, and you can actually see that from the chart, actually, we'll show that here in a second. But then there are materials kind of like concrete or like wood, like where they behave different under tension or compression. Maybe we'll take a look at some of those as well. So we have tensile strength, and then we have compressive strength. That's what they call it, right? Yeah, compressive strength. Let's like maybe abbreviate. And then we have shear strength. Okay, and when you have blue and purple together, blue and red together, that gives you purple, right? So here we go. Oh, whoops. Oh, lines don't go there. Whoops. There we go. And there we go there. So, okay. So steel. Steel is the same in tension and compression. So what we're going to see here is the ultimate strength of the material is given, and I'll just copy the numbers here from the book here, is going to be the same for the tensile and compressive. That's what I'm getting at here. So the numbers are going to be the same for steel in tension and in compression. And I should put the units on here. Units are going to be Newton per meter squared. In all cases here. Okay, so what does this quantity mean? Well, this is kind of the maximum amount of stress that you want to be on this material. Don't put any more stress than this amount of stress. Otherwise, you're going to start to deform the material. Okay, so for steel, we're saying at 500 times 10 to the 6 Newton per meter squared pressure, that's when steel is going to start to deform. What that means ultimately is that you're coming out of the linear region of that graph that we looked at the very beginning of the class. You come out of that linear region, that's when you enter into what I believe they call it the plastics region. If you have a steel beam in the plastics region, maybe you have something wrong there, right? The steel beam is starting to deform. All right, shear strength. Shear strength, not as big of a value. 250, about half as much. Okay, before the steel starts to really deform in that parallel direction to the applied force, and it's gonna start to break down. Okay, let's take a look at, let's look at one more metal here. So we just took a look at brass. Was it brass? Yeah, we looked at brass, right? In that problem that I gave from another book. So we had brass, and brass has 250 for the tensile. So that's in tension, right? So it's being pulled apart. And then also 250 in compression. And it's the same in tension and compression, again, because it's a metal. Metals tend to be like that. It just has to do with their atomic structure. And for the shear strength here, it's 200. So brass almost as good with the shear stress as it is in tension and compression. So those ones are all a bit closer. And then interestingly, we have aluminum, which is the same in all three here. So aluminum, it's 200 times 10 to the 6 all across the board here. So 200 times 10 to the 6, tension, compression, and shear, it's all the same. Okay. All right, let's take a look at maybe some more interesting materials now. We can take a look at wood. Is brass about the same for shear because it's softer? Yeah, so it gets a little bit tricky when you start talking about alloys. So brass is an alloy, right? What is brass? Tin and copper. Is it tin and copper? I can't remember exactly, but the atomic structure there is a mix now of multiple kinds of atoms. So some symmetry is broken by the fact that not all of the atoms are the same. So there's a couple different factors at play there, but it's not necessarily because it's softer. It's more to do with the molecular structure of the material. We have something like iron or steel. If you look, like for example, iron, I didn't write it here, but iron has the same tensile strength as it does shear strength, but its compressive strength is much larger. Yeah, I know what you meant by softer. I got you. Okay, so let's take a look at maybe something like concrete. So we looked at concrete earlier for a particular example. So for concrete, we have 2 times 10 to the 6 for the tension, and compression, it's far better. For compression, it's 20 times 10 to the 6. So 10 times as good in compression. That's why we build bridges in roads and things with concrete. Because when you put all the mass of those cars on top of the bridge or on top of the roads and stuff, and the bridge is arced slightly in a way so that it's in compression, it's much stronger than it is in tension. If there's any kind of bridge where you have some concrete involved and those beams, those concrete columns are in tension, you're probably going to run into some trouble at some point. And then again in shear, which is another thing you want to avoid with concrete, because it's also weak to shear forces. So the ultimate strength for shear force is 2 times 10 to the 6. So you don't want your concrete to be in tension, and you don't want it to have many shear forces on it. In terms of design of bridges, roads, buildings, and things, something that we might get to at the end of the semester is how materials expand when they're heated up. And that's very important when you're building like roads and bridges and things like that that are kind of long. And although if you have like a small piece of concrete and you heat it up, its length doesn't change much. If you have a really long piece of concrete and the sun is heating it up over the course of a day, that actual elongation due to heating can become relevant, and that can add shear forces, compression forces, and tension forces depending on the design. And so that's where you have to be really careful about how you design. If you go over some bridges, you'll oftentimes notice in the bridge there are these breaks in the bridge, and then there's another piece of the bridge here, and then another break, and then you have another piece like this, and you have these gaps here that allow for the material to expand when due to heating, so over a long period of time. And the reason for that is exactly what we're talking about in this chapter, to avoid fracture. Okay. All right, let's take a look at one more interesting material here. Wood, which is a very inhomogeneous material. What do I mean by inhomogeneous? That means it has almost no symmetry in the molecular structure. So we'll take a look at wood, and in particular, the book gives pine wood. And it says if we go parallel to the grain, or perpendicular to the grain, we have different values for the strength. Okay, so for parallel to the grain, the tensile strength is 40 times 10 to the 6. Now it says perpendicular to the grain, it gives no value here. Okay, it gives no value here perpendicular to the grain. I'm not sure why they do that. I think because it's difficult to have a force which is perpendicular to the grain, which puts the material in tension. Perhaps that's why. But parallel to the grain for compression is 35 times 10 to the 6. And they do give a value here perpendicular to the grain for compression. They give 10 times 10 to the 6. So we can see even within a single kind of material, we have different strengths depending on how we approach that material with our forces here. For shear, they give 5 times 10 to the 6 parallel to the grain. And then shear perpendicular to the grain, they give no value here. Okay, so again, I'm not sure why that is. It could be because it's difficult to even get shear stresses that are perpendicular to the grain. But there it is. That's what we have there. Okay, so that's just kind of an overview here of just the strength of materials, right? So what do we do now to solve problems? Because there are going to be a couple problems. There's a thing called safety factor that your book talks about. And what a safety factor is you take the ultimate strength of the material and you divide it by the safety factor. So if you're looking at the maximum, I should put stress here. So the maximum stress given a safety, let's be super particular here. So the stress, so max, okay, actually we can just write it like this. So max stress given a safety factor, let's abbreviate here, SF, not San Francisco, but safety factor here. So the maximum stress given a safety factor is the ultimate strength divided by the safety factor. Simple as that. So take the ultimate strength, divide by the safety factor. So if I have a steel beam, so example here, if I have a steel beam in compression, with a safety factor of, let's say, 4, then the maximum stress would be, I take the ultimate strength and I divide it by 4. I have to scroll up here, steel beam, right? Here's steel. There's the compression factor there, 500 times 10 to the 6. I scroll back down, 500 times 10 to the 6. And that's newtons per meter squared, or pascals, right? And we just do that division. That's 125 times 10 to the 6 Newton per meter squared. So for safety reasons, we don't go all the way up to the ultimate strength, right? That just makes sense, because once you reach the ultimate strength, that's when you start to see deformation. So you insert this safety factor here, and the safety factor divides the ultimate strength of the material, and what you're left with is the allowable stress. That's what they call it, the allowable stress given the safety factor. Okay. There's an example here, and maybe we can just use the last couple minutes of class time to do another example. So maybe I can pull this out a little bit. Kind of leave the, oh wait, what happened? Oh, somehow Oops, I accidentally deleted what I wrote down before, guys. So should I just rewrite it here, or did everybody have a chance to copy that down? So let me maybe quickly rewrite it. So max stress for that steel beam was equal to the ultimate strength, 500 times 10 to the 6 Newton per meter squared, divided by the safety factor of 4, and so we get 125 times 10 to the 6 Newton per meter squared. Okay. All right, the example that is given in the book is breaking a piano wire. So steel piano wire is 1.60 meters long, has a diameter of 0.20 centimeters. So we're going to use that to calculate the area, right? And they ask what force would break the wire. Right? So the maximum stress, the ultimate strength of the material, that's a force over the area, right? So if we want to know the force, then we have to calculate the force based on the maximum strength. In this case, there's no safety factor in this problem, but we could ask the question like, okay, if we have the safety factor, what's the maximum amount of force we should apply? But simply the max stress is going to be equal to the ultimate strength of the material with no safety factor. So we're not dividing by 3 or 4 or 5 or anything like that. And that is going to be equal to the force over the area. And a piano string is something that's in tension, right? It's definitely in tension. So the ultimate strength here that we're going to use is the tension, ultimate strength for steel in tension, which is 500 times 10 to the 6 Newton per meter squared. And we can take this and multiply by the area to get the force. So the force is equal to the ultimate strength times the area. And the area is pi d squared over 4, or pi r squared, right? Area of a circle. The cross section of a wire is going to be a circle, right? We want to make sure we convert. I'm going to make sure we convert our units here. So let's go ahead and plug in the diameter here. So 0.2 times 10 to the minus 2 meters. And we square, we square that right there. And what we end up for when we crunch the numbers on this is about 1600 newtons. So just double check that you can reproduce that answer there on your calculator, right? Make sure you understand that. That is an example just right after this table in the book on page 245 in the textbook. So you can take a look at that. That pretty much covers everything that we need in this chapter. There is a famous kind of engineering disaster that's talked about in the textbook, conceptual example 9-12. So conceptual example, let me just give you the page. So it's on page 246 in the book. There is a conceptual example. And this is a really famous disaster, engineering oversight, where an engineering firm designs a building And what ultimately happens is their particular design is safe, but the manufacturer of the materials, um, based on their factory where they make the materials, they're not able to create beams which are long enough for the design of the engineer, right? And so they suggest a change to the design. And that suggestion ultimately is not double checked by the engineer. So the engineers, well, the engineering firm or whatever, whoever's in charge, okays the new design without actually going back through and recalculating and making sure that it's safe. And to, like a naive person who's not, super experienced with these kind of, designs, and this is kind of typical of maybe people, 50 to 100 years ago. I can't remember when this was. Okay, this was about 40 years ago, actually. So, so maybe like people aren't as experienced with building these tall buildings just yet, right? And so this design flaw kind of made it through the checks. Nobody really verified that it was still safe with this minor change in the design. And it really is a minor change in the design. When you go and you look at it in the book, you can see it's like, this looks almost exactly the same, but it's really not when you go in and analyze the problem. And ultimately what happens is I think 100 or so people actually were killed in the collapse of one of the floors of this building. So there was some sort of like tour that was going on. And so there was like a bunch of people kind of like touring this new building, and it's supposed to be some extravagant thing. And because of this engineering oversight, the building like starts to collapse and people are dying because of it. So a lot of things that seem like small changes can oftentimes make a big difference in terms of the forces and things that are acting on certain beams in a building. That's why there's so many checks. That's why it takes so long to get approved for buildings to be put up and things like that. Everything has to be triple, quadruple checked. Anyways, we're like 6 minutes over, so we're going to go ahead and end things there. Feel free to stick around if you have any questions for me. Hopefully everything was clear there today. We didn't get a chance really to review the stuff from last week, but I think we did a ton of examples last week, and we did, I think, a lot of examples today as well. So hopefully this chapter is like a high point in terms of like the overall grades and stuff for your guys' homeworks. So do remember that there are, homework part 1 and part 2, and then there's the quiz on Friday as well. So feel free to leave the meeting if you don't have any questions for me. But if you want to stick around and ask some questions, I'm here.